Hi, in this video I will show how to solve a fun little factorial equation with prime numbers. Here's the problem. Find all primes p such that p to the a plus p to the b equals n factorial, where a, b, and n are positive integers. So without loss of generality, we can assume that a is greater than or equal to b because of symmetry. And for convenience, we'll set c equal to a minus b. This means we can rewrite our equation as p to the b times p to the c plus 1 equals n factorial. We also note here that since p is greater than or equal to 2, we know that n must be strictly bigger than 2. So we are going to solve this by dividing it into three cases. Case 1 will be for p equals 2. Case 2 will be for p equals 3. And case 3 will be for p greater than 3. Case 1, p equals 2. So our equation is now 2 to the b times 2 to the c plus 1 equals n factorial. We'll start by reducing our equation modulo 3. Now since n is at least 3, we know that n factorial has to equal 0 modulo 3. Now, since 2 to the b can't equal 0 modulo 3, we know that 2 to the c plus 1 must equal 0 modulo 3. And you can check yourself, but this only works if c is odd. So what we're going to do now is we're going to check two cases by hand for n equals 3 and n equals 4. And then we're going to rule out all other cases for n greater than or equal to 5. So I won't go through the steps, but a quick check by hand produces two solutions, one for n equals 3 and one for n equals 4. For n equals 3, a equals 2, b equals 1 works, since 2 squared plus 2 equals 3 factorial. And for n equals 4, we have a equals 4, b equals 3, and n equals 4, which is also a solution, which gives us 2 to the 4th plus 2 to the 3rd equals 4 factorial. And you can double check those by hand if you want. So now that we've checked by hand n equals 3 and n equals 4, we can assume that n is greater than or equal to 5. And now we note that n factorial equals 0 modulo 5, since it's at least 5. And by the same argument we had above, we know that 2 to the c plus 1 must equal 0 modulo 5. This only works if c is even. Again, something you can check by hand. But this is a direct contradiction to our result, looking at modulo 3, which said that c had to be odd. Thus, there are no solutions for p equals 2 and n greater than or equal to 5. Now we go on to case number 2, for p equals 3. Our equation is now 3 to the b times 3 to the c plus 1 equals n factorial. So now we're going to check n equals 3 by hand, and we find the following solution. A equals b equals 1, n equals 3, because 3 plus 3 equals 3 factorial. So that's the only solution for n equals 3 and p equals 3. So now we assume that n is greater than or equal to 4, and we're going to reduce modulo 4. And note that, once again, n factorial equals 0 modulo 4, because n is at least 4. And by arguments we made earlier, we know that 3 to the c plus 1 must equal 0 modulo 4. And so again, you can check by hand, but this only works if c is odd. So now we're going to do something we did similar before. We were going to check another case by hand for n equals 4 exactly. And we find that there'll be no solutions for n equals 4 with p equals 3. So now we assume that n is at least 5, so n is greater than or equal to 5, and now we reduce modulo 5, like we did before. And again, that means that n factorial is 0 modulo 5, and again, that means that 3 to the c plus 1 is 0 modulo 5. Breaking down the values of c is a little more complicated. I leave that to you to do by hand, but you should find that c needs to equal 2 plus 4 times m, where m is a positive integer, in order for 3c plus 1 to equal 0 modulo 5. But clearly, if c equals 2 plus 4 times an integer, then c is even, and this is a contradiction to a result modulo 4, which said that c needed to be odd. So we have no additional solutions for p equals 3. Our final case is for p greater than 3, and we're going to show that there are no more solutions quite easily. So if we look at our original equation again, p to the b times p to the c plus 1 equals n factorial, it's clear that p must divide n factorial. The only way a prime number can divide n factorial is if that prime number is less than or equal to n. And if the prime number is less than or equal to n, then p minus 1 is strictly less than n. So for convenience, we're going to call p minus 1 m. We said m equal to p minus 1. And it should be pretty obvious that means that p equals 1 modulo m. And what we're going to do is we're going to reduce our equation modulo m now, which is actually p minus 1, but we're just calling it m for convenience. So if we reduce our equation modulo m, we see that p to the b times p to the c plus 1 is actually equal to 2 modulo m. So the left-hand side of our equation is equal to 2 modulo m. However, m is strictly less than n, so that means that n factorial equals 0 modulo m. But this is a contradiction. It can't equal 2 and 0 modulo m. Thus, there are no solutions for p greater than 3. Thank you.